Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased point of view, of course. So take everything with a grain of salt. Well, today's theorem, I will be very sketchy about the theorem itself because the theorem is based on a very classical construction, which are the p-adic integers or the p-adic numbers. I wasn't quite sure whether I should call this video p-adic integers or p-adic numbers. They're kind of the same, like the integers and the rational numbers. We'll see. Anyway, so I will be a bit sketchy when it comes to the theorem itself, but it's kind of the idea that you want to solve a polynomial equation and you usually can't do that because it's a polynomial equation. And maybe you can solve it in a different number system, and this will tell you something about your original question, like you want to find rational solutions to your polynomial equation. It turns out that a very useful number system or very useful number systems in this sense are the so-called p-adic integers. So that was the original motivation to introduce them. Like they're kind of a power series version of integers, if you want. We will see. Um, and yeah, so they also then turned out to be extremely useful in other parts of mathematics. And nowadays we have something like p-adic analysis, so analysis of the p-adic integers or p-adic numbers. You have p-adic geometry, which has been very popular for in the past whatever years. So it's very popular nowadays, for example, and other flavors of kind of the same thing. And everything boils down to, and that's kind of the point of this video. Well, climbing infinite trees. So I took this idea from two very nice, one very nice article and one very nice presentation, which are linked down in the description. And yeah, so this is the approach I want to take to explain what p-adic integers are, and then later what p-adic numbers are, and then the theorem I have in mind. I want to think of an infinite tree, like growing from a root all the way to, well, kind of infinity. If you squeeze it a little bit, it would fit into, let's say, a finite rectangle. Then it looks a bit like a little fractal. So the idea is very simple. So you fix a prime. So p will always be a prime, and I want to construct this beast here, the p-adic integers. And the way I would like to do this is, well, as I said, I have this tree. This is this picture up here, and I start at a root somewhere. And depending on my prime, so p is 3 in this picture, I have always this number of branching points. So I have a branching, a green branching, I have a red branching, and I have this whatever orange type branching corresponding to the remainders on division mod 3 in this case, 0, 1, 2. And I keep on going. Red, orange, 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 red, 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 and green, 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 green. I keep on going. And I want to think of a p-adic integer as kind of a walk in this tree until you hit a leaf. You will really never hit a leaf in some sense because, well, the leaves are at infinity. So it will be the p-adic integer is an infinite walk. But basically that's the idea. So I will write them down as follows, like this one here. So the little 3 is just a reminder that my chosen prime is 3. And then I just, well, uh, whatever. I had orange here. So orange was 2. So 2. And then I had green, which was 0. And then I had orange again, which was 2, and so on. And it's just remembering where I walk along the along the tree, right? So 2 to 0, to 0, red. The only tricky point is I like to read them from right to left because I kind of want to think of them as being, we will see, as being a reversed version of writing down decimal expressions of real numbers. Anyway, so 2, 0, 2, and then you could go on forever, like 1, 0, 1, 1, 1, 2, 1, whatever, something like that. So you just write down a sequence of those symbols, 1, 1, 2, 3, whatever, something like that. Just really an infinite tree, and any kind of, it goes on forever, and any kind of sequence corresponds to a p-adic integer. And the interesting, well, there are many interesting points about p-adic integers, but maybe the interesting starting point is that you actually have a notion of a distance on this tree. And okay, you want to be at 1 over p to the k, and the k is really the interesting point. Well, the 1 over p is of course also interesting. You want to make things small if they have a lot of zeros. You will see it in a second. But anyway, so the main crucial point here is this k, in my opinion, because the k is this combinatorial property that basically tells you how far two walks are apart. And if you think about how far are two walks apart, well, let's say I walk to somewhere and you walk to somewhere else, then you would measure it from the point where we diverge. And that's exactly what we do. So I have this walk from before, this 2, 0, 2, and so on. And I have another walk, which is this 2, 0, 1, and they diverge at this vertex. So I just measure the distance to the origin, and that's the distance. Well, 1 over 3, because remember p over 3 here, that's the distance between those two paths. In particular, that's what I was trying to say before. If you have the 0 path, right? So 0, 0, 0, 0, 0, 0, 0, which will play the role of the 0, is very close to everything that starts with a lot of zeros. Because, well, let's say here's a 1. The further this thing is away, so we have 4 here, 0, 1, 2, 3, 4, so this is position 4. So let's say p is 3, then the distance between those two things, the 0 element and this walk, whatever, no matter how it continues, would be 1 p, so p would be 3 to the 4. So the bigger this number k gets, of course, because I take 1 over p, the smaller this gets. So it goes to 0. So if you have a long string of zeros, this goes to 0. And you're very close to, well, the 0 point in this, well, tree-like, or whatever, number system. It's not yet a number system. It will be a number system in a second, but right now it's not really a number system. This tree-like combinatorics. And yeah, and then you can talk about whatever unit balls and so on, because this really is a metric. So you can check that this is a metric. You have the notion of metric spaces and so on. So from here on, you can go and do some kind of metric system. What we do with a metric system, you define topologies, you might want to define some version of analysis and so on and so on. But what is still a little bit missing is, well, why do I actually call them integers or numbers? So there is no addition or multiplication that is absolutely visibly obvious from this picture, but there is actually one. And well, so the only, let me change to p equals 7 because it's a little bit more illustrative. So addition 7 adically in this picture, of course, in general, then p-adically. So we already have a metric, check, and we have an addition, as I will going to explain, so check. And if you have an addition, you have a multiplication, because multiplication is just iterated addition. In particular, in this setup, because by addition will be just a standard addition that you know from, well, the integers. If I have addition, I also have kind of subtraction. And division is a bit trickier, so I don't want to talk about division too much, but you also have division. Anyway, so as I explained, those 7 adic numbers are those sequences with symbols from 0 to 6. So here it was symbols from 0 to 3 because 0 to 2 because p was 3. So this is always p minus 1, so 0 to 6. And you just can do the naive, the completely elementary and naive addition of those numbers. So here I have my top number, and which is this infinite sequence. And here I have my bottom number, which is this infinite sequence. And well, that's also the reason why I want to write them from right to left, because now I can just apply naive addition, right? 2 plus 3 is 5. Very good. So I write 5. 1 plus 0 is 1. Very good. So I write 1. 4 plus 1 is 5. 1 plus 1 is 2. 5 plus 2 is 7. Oh, but we are doing kind of a mod 7 thing. So the only difference is now I would write 0 instead of 7, but I still take the carry. Okay. Well, I take then the carry because kind of I want to think of something being 7 adically here. And then I have 1, 2, 1, 4, and you continue. Right? So the only difference, I really just naively mimic addition, the usual addition. The only difference is whenever I hit 7 in this case, so p, instead of as you are used to 10, I write 0 and I get a carry, right? I write 0, get a carry. You can do naively subtraction in the same way. In particular, if you would subtract something like 1, this is my notation for 1. In this sense, it's just 1, a lot of zeros, right? 0 was 0 and a lot of zeros. 1 is 1 and a lot of zeros. And you can subtract it from 0, which should give you -1, right? 0 minus 1 should be -1. You just do this naively. And what you would usually write here is 9, right? But now we're doing everything over p equals 7. So I read 6. I get a carry, and I get 6 again instead of 9. I get a carry, I get 6 again, blah, 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 and so on. So actually, in this number system, -1 is this infinite sequence of 6s, so p minus 1s, all the way up to infinity. Yeah, and that's kind of fun already, but it should remind you of something like this. So if you write down decimal expressions of, well, let's say the usual numbers, you end up with this ambiguity that, well, let's say 1 is equal to, as I wrote it here, 1 is equal to 0.9.9.9, and so on. Let's say base 10, whatever. And of course, they are the same. And this is kind of the same pattern, right? -1 is equal to this lots of zeros. This is really the analogy here. Anyway, so all this slide is saying is that actually you have a multiplication. And with multiplication, you have a subtraction. And now you shouldn't be too surprised anymore that you also have a multiplication, because you can just mimic. So the elementary multiplication is just a repeated addition, right? It looks a little bit like this. If you want to multiply two numbers, a and b, whatever, a times b, then you write down all of these things that you add then together. Try to remember your, and then you get the result c, whatever. Try to remember my old days in whenever I learned that. I don't remember anymore. And of course, I don't do it this way anymore, so that's why I don't remember. But yeah, so this is kind of the standard elementary way of how to multiply things. Just the only thing you need to know is this recipe and addition. And I already told you that addition is also elementary. Only difference is you always, whenever something hits p, you turn it to 0, and you might worry about the carry. That's the only difference. Anyway, so what do we have? We have a metric, so a topological space. We have an addition. We have a multiplication, so a ring. So we can put everything together. So here's this nice picture I stole from the article. I will explain the picture in a second. The article is really good. I say it again. It's linked in the description. Anyway, so we have a metric and an addition. And basically this means we have a ring with some topological structure. And so we could define, and here's a formal definition, or two formal definitions, the p-adic integers or the p-adic numbers. So the p-adic numbers is qp and the p-adic integers is zp, via two equivalent definitions, either the algebra definition that I basically gave you. In terms of formal algebra, it looks like it's the inverse limit of z, p to the n z. And then the qp is just a field of fractions. It's exactly the same relationship between z and q as there is the relationship between zp and qp is the same as the relationship between z and q. One of them is the field of fractions of the other, and the other one is a ring of integers of the other. So this is the algebraic construction. If you don't like that because you're unsure what this inverse limit is, it doesn't actually matter. The inverse limit is just a formal way of describing what I did before with this walks on those trees. But it also doesn't matter in the sense that there is another way of constructing those number systems, which is equivalent, but maybe a little bit easier to think about. At least I like it a lot. So if you think about how R is constructed, so real numbers. They are constructed by taking Cauchy sequences with respect to the usual distance in Q, and you mod out by nil sequences. So same in Q. And you do exactly the same to construct the p-adic integers, the p-adic numbers. You take Cauchy sequences, but now with respect to this funny distance, and you mod out by nil the sequences. And the ring of p-adic integers is then just a ring of integers. So really, this is the analogy I would like you to keep in mind. So those are really constructed like the real numbers. And that's why also you shouldn't be super surprised that these things actually, they look pretty small, but they are not. They are uncountably big if you care for set theoretical sizes. So ZP and QP are both uncountable sets. So uncountable rings or fields. So QP is a field and ZP is a ring. Right? And both of them has this nice topology coming from exactly in the same way how R gets in topology from this construction, Cauchy sequences modulo nil sequences. And the picture, before I explain my theorem that I actually was going to talk about, the picture here is, as I said, stolen from the article linked in the description, and it's exactly the same idea. Instead of climbing trees, which what I did is they decided to climb towers. So if you have seen my thumbnail picture, there were those circles, and then you got circles in circles in circles in circles, this fractal-like structure, and you could think of them as pushing upwards. So this is how you get this picture of a tower, and then it's climbing a tower instead of climbing a tree. But it's really the same idea. It's just kind of a fattened version of the tree. And that's, I said again, that's where I stole it from. Link is in the description. Anyway, so let's go to actually the theorem. It's sometimes called the local global theorem. And I don't want to go too much into details. And the crucial thing here, so link is of course in the description. The crucial thing here is that I'm not really precise what I mean by nice. But kind of the idea is the following. It's a local global principle. So you want to solve a polynomial equation over the rational numbers, because that's what mathematicians have done for 2,000 years, like Diophantine equations. You want to solve them over the rational numbers. And this is just hard. What is easy to see is, because you have this construction, so those completely equivalent constructions, actually Q sits inside, okay? So if this holds in Q, so you get a solution in the rationals, then you get also a solution in R and in QP for all P. This is kind of, you have a global solution, and then you get local solutions, right? If you want. That's rather uninteresting. The point about the local global principle is the converse, which only holds, so this always holds, so A always holds, and the converse holds only for certain types of equations, for certain reasonable types of equations, let's say it this way. But the converse is, of course, you could solve the equation in R and in QP, and in R, it's usually very easy to solve those equations. And in QP, people have come up with kind of methods to solve them. The point is you have those local solutions, and you can piece them together to the solution they're really interested in, the global solution in Q, right? Local global principle. And that has played, this is actually already pretty old. So 120 years at least. And yeah, it has played a huge role in number theory, for example, and in also other parts of mathematics. So nowadays, as I said, there are ideas of p-adic analysis. Well, you can do analysis, of course. Why? Because we have those metrics here. So yeah, you should be able to do some kind of analysis. It's also, those things are also uncountable, so well, very good space to do analysis. And you also can do some fancy algebra or geometry because you have this algebraic definition. So kind of those are the two things people like to study nowadays about. So nowadays it's 2021, but I don't think this changes a lot in the next whatever years. Anyway, so people nowadays like to study p-adic analysis and p-adic geometry, p-adic algebra. So let me finish by showing you a fun application, what you can do with in p-adic analysis. So for example, square root of 2. So does square root of 2 make actually sense in my p-adic integers? Sorry, in my p-adic numbers. QP. It actually, in the end, makes sense in p-adic integers, as we will see here. So there's a period here. So kind of the integer part is everything from here onwards. This was my infinite tree. And in order to add the rationals, so the p-adic, the inverses, you kind of put a comma. So it's kind of the opposite what you would do for a decimal expression of a real number. So for a decimal expression of a real number, you would have infinite symbols to the left, infinite to one side, and finite to the other. Finite symbols, infinite symbols, finite symbols to the right, and infinite symbols to the left. And for those p-adic things, it's different. You have finite things to the right, yes, and infinite things to the left. It's kind of reversing everything. Anyway, so square root of 2 actually is already in ZP, but anyway, in particular, it is in QP. And the way to see this is to use Newton's method from classical analysis. So you can approximate solutions to x squared minus 2 using Newton's method. So I stole this from Mathematica, and basically I will show it to you in a second. So the link to the notebook is of course in the description. And what it compares is how you do it over R here and how you do it over QP. So this is QP here. And this is just a check as it says that actually it works. So it's this iterative process, Newton's method. If you don't know what it is, it's you approximate your solution. You choose a starting value, and you try to approximate the solution to this equation by using some iterated process on the solution. So there's some n, so some repeated process. So n goes up to 4 here. So this is your starting value, and of course that's always the same. Well, the square of the starting value is 12, which is a bit off from what you actually want, because you want it to be 2, as you can see. And then you iterate, and in each step you get better and better. So xn is the next one, next one, next one, and this already looks very much, so this is also R. This is just as a fraction. This already looks very much like square root of 2, right? So this as a fraction, it's this one. And p-adically, you can do the same. So actually, let's have a look at Mathematica. So here's a promised Mathematica demonstration with a link in the description. And it's really just what it says, Newton's method for p-adic integers. And you can choose which one you want. So you have 3 options, square root of 2, square root of 3, or the golden ratio. And it also tells you what kind of things are very nice. But anyway, let's stay with square root of 2. So what you can do here is you can change your starting value, or you can change the prime, right? Like you could go to 5, you could go to 7, to 3. Let's have a look at 3. As you can see, for 3, this method actually doesn't work. Okay, it doesn't work. How can I see this? This number here is certainly not 2. 2 would be 2.0. So let's have a look at 7 again. 2 would be 2.0. And this 1, of course, moves all the way up to infinity as you iterate. So for here, it doesn't work. Here, it doesn't work. Here, it does work with the starting value 3. So that's kind of the whole point about p-adic analysis in some sense. So it's on the one hand very similar to analysis, so you can play the same games, but as you would do in analysis. But there are some subtle differences which makes this really interesting. So let's have a look again at 3. So this doesn't make a difference for the real part here, and it's still converged in the same rate. But here you just don't have any convergence, or this is very far away from 2. With 5, same problem. Here doesn't change. With 7, then it actually works. And I can also vary the, let's say, the starting value. And as you can see here, it's a real part. It still converges, very nicely. So this is roughly square root of 2. And here it also works. But again, for 5, this is pretty messy. For 7, this is good. And those, for example, it also tells us that for 17 and starting value 6, it should be, oh yeah, it should be very good, as you can see. And again, this doesn't really care. So there are some subtle differences. Okay, so let me wrap up. What I wanted to tell you about is the local global principle. This idea that you can solve equations locally, which means in this case over R, which is usually easy, or over those p-adic numbers. And then you get a solution that you really care about, namely over the rationals or the integers. And in order to explain what this actually means, I try to explain in a hopefully reasonable way what p-adic numbers and p-adic integers are by using this picture of an infinite tree that you just walk along. And then in the end, what is the outcome are those p-adic numbers, p-adic integers, whatever, and they just are very important in whatever p-adic analysis or p-adic number theory or p-adic representation theory, p-adic geometry, something like that. So there are a lot of p-adic analogs of some kind of classical parts of mathematics. Anyway, I hope you enjoyed the video, and I also hope to see you next time.